This presentation is delivered by the Stanford Center for Professional Development.
Great. We'll start in on our next application topic, which is statistical estimation. So last time we looked at estimation from I guess just a purely, just sort of a simple fitting point of view, approximation and fitting. And now we'll actually look at it from a statistical point of view. Actually, it's interesting because you end up kind of with the same stuff. You just get a different viewpoint. So let me give the broad setting is actually just it's just pure statistics. So here is pure statistics. It's this. You have a probability density that depends on a parameter. So that's pure statistics. And I guess our stat department, there we go, contingent. Oh, and their center front will keep me honest, or at least object when needed. So in pure statistics, there's just parameterized probability distributions, and we have a parameter x, and your job, you sample you get one or more samples from one of these distributions, and your charge is to say something intelligent about which distribution, which is to say which parameter value generated the sample. So that's statistics. So a standard technique is maximum likelihood estimation. In maximum likelihood estimation, you do the following. You have an observation y, and you look at the density of you look at the density at y, or probability distribution if it's a distribution on if it's got on different points on atomic points. You look at this and you actually choose the parameter value x that maximizes this quantity. That's the same as maximizing the log likelihood. We'll see actually why the log goes in there. The log goes in there for many reasons. One is if you have independent samples, this splits into a sum. And the second is that many distributions are actually log concave, this time in the parameter. Now, in fact, last time, so far we've looked at distributions that are concave in the argument. This is concave actually in the parameter, and those are actually slightly different concepts. So we'll see this in examples. All right. So the log of I'll just call it a density. The log of the density as a function now of the parameter here, not the argument here. This is called the log likelihood function. And in this problem, it's often the case, for example, if some of the parameters involve things like variances or covariance matrices, or they're just parameters that are positive or something like that, if they represent rates or something intensities, they're clearly limited into some set. So you can add to this problem either an explicit constraint, that part that x has to be in some set C, or another way to just effect the same thing is simply to define p sub x of y to be 0 when x is outside the domain of the domain of p, at least the parameter argument. And that, of course, makes the log minus infinity, and that makes it a very poor choice if you're maximizing. So that's the same as just making the constraint implicit. Okay. So these are very often convex optimization problems. By the way, they are sometimes not. If you do machine learning or statistics, you'll kind of you'll get a feel for when they're not. Typical examples would be missing. The most obvious and common example is missing data. But we'll see some examples, and we'll focus on the cases where it is. So this is often a convex optimization problem. And remember, the variable here is x, which is a parameter in the distribution. Y here actually is a sample. It's an observed sample. Okay. Let's look at some examples. The first is just linear measurements with IID noise. So here's what you have. You have a bunch of measurements. So you have yi is ai transpose x plus vi. Here, x is the set of parameters that you want to estimate. But I guess if you're a statistician, you would say the following. You would say that the data yi are generated by a distribution. The distribution is parameterized by x. Okay, so that's what it is. And the way it's parameterized is this way. And in fact, x only affects, as you can see, the mean of the distribution. It doesn't affect, for example, the variance. But that doesn't have to be the case. So, I mean, the way a normal person would say this is x is a set of parameter values that you want to estimate. But this is fine. The conceptual way to say this is you have y is generated from a distribution parameterized by x. Okay, so we'll take the VIs to be IID measurement noises, and we'll let the density be P of z. So we're just going to make this scalar. It's easy to work out what happens in the case when these are vector measurements. It's very easy to do. Okay, so the density, I mean, of this clearly is simply you take yi minus ai transpose x, and that of course has this density, and they're independent. So the probability density, if you fix x, this is the parameter, it's just simply the product of these because they're independent samples. So you get this. That's the density. You take the log of that, that's the log likelihood function, and you get this thing here. So this is maximize. You know, I think I'm missing a sign or something here. No, I'm not. Everything's fine. Sorry. So your job, you take the log of this, it splits out, and you get the sum of the log of these probability densities, and your job is to maximize that. So for this to be a convex problem, in the general case, in x, remember yi are samples, they're data. X are the variables here in an optimization problem. What you need to happen is you need p, in this case, because this appears in p, that's affine in x, you need p to be log concave. So in this case, because the parameter appears affinely in p, it's good enough for p to be log concave for this to be a convex problem. So let's look at some examples. Here's one. If the noise is Gaussian, so the density is just this. It's nothing but that. Then the log likelihood function looks like this. It's a constant here, it has nothing to do with x, and then minus this term, but if you look at that, it's a positive constant times nothing but sort of an L2 residual, right? So nothing else. So in this case, the maximum likelihood estimate is the least squares solution. So now you know, if you're doing least squares, you're actually doing maximum likelihood estimation with assuming that the noises are Gaussian. And in fact, it doesn't matter what the variance is. Oh, sorry, all the noises have to have the same variance. If you do maximum likelihood estimation and the noises of the different measurements have different variances, what does that translate to? Yes, it's weighted least squares, of course. It's diagonally weighted least squares. So that's what you do. So you can turn it around. And if you're doing diagonally weighted least squares, the truth is you're doing diagonally weighted least squares. If someone asks you, you could say because I trust that measurement more than I trust that one or something like that. But if a statistician friend stops you and says, what are you doing? You say, I'm doing maximum likelihood estimation with the noises here having different variances. So that's what that means. Okay. That's fine. So now you know what least squares is. Has a beautiful statistical interpretation. Let's try Laplacian. So in Laplacian noise, it looks like this. It's exponential. And you actually can say a lot of things about this compared to a Gaussian. The most important by far is that the tails are huge compared to a Gaussian. So e to the minus x squared is a whole lot smaller than e to the minus x when x is big. So this has huge, huge tails. I mean, obviously the distributions with huger tails, however, those distributions are not log concave. But nevertheless, so that's the main difference here. If you do this and work out what this is, actually all you're doing is just this. You're just maximizing the sum of the log of the probability density. You get a constant, that's from this thing, and then over here you get a positive constant times the L1 norm. So that's what you're doing. So if you do L1 estimation, then what you're really doing is you're doing maximum likelihood estimation with Laplacian noise. So, and this sort of makes sense actually. This makes sense that this is why L1 estimation, and you know what L1 estimation does. What L1 estimation does is it allows you to have some large outliers where L2 estimation would never allow you to do that. In return, it will actually drive a lot of the smaller residuals to zero, for example, to zero or small numbers. So, and now you can actually justify it statistically. You can say, well, you're really assuming that the noise, in this case, is more erratic. You're saying that, in fact, V does not fall off like a Gaussian. If something falls off like a Gaussian, then being 6 sigma out is actually a very, very unlikely event. And you will change X considerably to avoid a point where you're actually making the estimate that one of these things is 6 sigma out. Okay? If this is Laplacian, you are much more relaxed about that. It's a rare event, but it's not essentially, for all practical purposes, an impossible event. And you'll actually allow a large outlier there. And so it all sort of makes perfect sense statistically. As another example, you have uniform noise. So suppose the noise is just uniform, which is interesting because it basically says this noise here, it cannot be bigger than in absolute value than A. Absolutely cannot be. On the other hand, between minus A and A, you have absolutely no idea. You're just completely uncommitted as to what its value is. It's not even centered at, it's centered at 0, sorry, but it's not concentrated at 0. It's not more likely to be small than it is to be large. It's completely uniform in there. And sure enough, the log likelihood function is this. It's minus infinity unless all of these measurements are consistent sort of within A. They have to be. But then it's just a constant. So here, the log likelihood function actually takes on only 2 values. It's a constant, and it's minus infinity. So any point inside this polyhedron is a maximum likelihood estimate. Okay? So that's the that's what happens here. And of course, it's not unique, and so on and so forth. And if you were to add to the uniform noise even the slightest tilt towards the center, you might get something else or something like that. So what this does is it allows you to translate or to talk statistically about your fitting, your penalty function. So for example, let's do one. Suppose I told you, suppose I'm doing fitting and I'm using a penalty function that looks like this. Okay? So it means I don't really, if your residual is within plus minus 1, I don't care at all. It's fine. I'm not even interested. Once it's between an absolute value less than 1, it's fine. Then it grows linearly. And so I want to know, what's the statistical interpretation? This is maximum likelihood estimation. What noise density? What's the imputed noise density here? What would it be? This is maximum likelihood estimation. So what? This corresponds exactly to maximum likelihood. What is it?
It's uniform in the middle and exponential tail in the tail.
That's exactly it. Yeah. So if you're doing dead zone linear penalty, which you could do and just defend it on any, on very simple grounds and say, well, look, if the residuals, look, I can't even measure it that accurately. So if it's between plus minus 1, I don't even care. That's fine. That's as good as my measurements are anyway. It makes no sense. And then you say, well, what about linear? Why not quadratic out here? Linear would say something like, well, sometimes there are some pretty large residuals or pretty large errors and things, and that's why I have this linear and not quadratic. Okay? So that would be it. The statistical interpretation is exactly this. You're doing maximum likelihood estimation of y equals ax plus v. The vi's are IID, and they have a distribution that looks like this. That's supposed to be flat, by the way. No, I don't know. There, okay? So it's a uniform distribution between plus minus 1, and then it falls off. It has exponential tails outside. So that's what you're doing statistically. Makes perfect sense. Here, you'd adjust everything to have integral 1, of course, but that makes no difference, in fact. It's just that's the shape of what you have. So if you do uniform, oh, and by the way, this is, of course, log concave because the negative log of this is that. And in fact, that's how that's how this came as by flipping this and then taking the exp. Okay? So that's how that works. So that's all you do. So this is it. Okay. Okay, so there's more on that, but that's something you can do in homework and reading and stuff like that to sort of see how that works. And this is a very simple case. You can actually get to the case where you're estimating things like covariance matrices and things like that, or other parameters, and it's actually more interesting, but that's the basic idea. Okay, let's look at another an example of something different, where the noises are not additive at all. They enter in a complex nonlinear way. So we'll look at logistic regression as sort of a canonical example of this other of other classes of maximum likelihood estimation problems that are convex. So let's look at that. I have a random variable that's in 0, 1, and its distribution is the following. It has a logistic distribution, so the probability that y is 1 is e to the a transpose u plus b. It's e to a number divided by 1 plus e to the number. So that looks like this, I guess, if you plot this function like that. So that's 0. And what this says is, so actually let's even take a look at this. If this, for now, just treat this as a number, a transpose u plus b. If this number is, let's say, 0, it means that's sort of the equiprobable point. It says that the probability that y is 1 is half. If a transpose u plus b is like 2 or 3, then this is very likely, but not perfectly certain, to be 1. And if this number is, say, minus 2 or 3, this is also, it's very likely to be 0, but not quite. So the transition zone is where this number is, let's say, between plus minus 1. I mean, you can choose that number some other way. But roughly speaking, when this number is when this number is 0, that's the equiprobable point. When this number is between, I don't know, plus minus a half, plus minus 1, you know, you can throw in your favorite number in there. The probability is some sort of number like, 10%, 90, between something like that. You could work it all out. When this number is things like 3 and 4, this is overwhelmingly probable to be 1 here. And if it's negative 3 or 4, it's overwhelmingly probable to be 0. And that's sort of a picture like this. Okay? Now, I guess to the statistician, here, A and B are parameters. So those are just the parameters that generated the distribution. And so our job is going to be to estimate A, and B. Now, you can't estimate A and B if I just give you one sample from this. So you're going to be given multiple samples. In other words, I'll give you a bunch of samples, and for each sample I'm going to give you U. So U here these are often called explanatory variables. So they would be other things that you measure and associate with this sample. So this would be, for example, I don't know, if you're admitted to a hospital, this would be things like blood pressure, weight, blood gas concentrations, all things like this. And this could maybe be if you died or something like that, right? So that would be that. So yeah, hopefully things will end up over here. All right? So that's it. All right? So, okay. So that's what this is. So these are explanatory variables. And what you want to estimate are the parameters A and B that parameterize this distribution. Okay, so what we'll do is we're given a bunch of samples, and a sample looks like this. It's a pair, UI and a YI here. These are people who checked in, and this is what happened to them. I guess in this case, 0 being the good outcome. Well, we have to decide, but we'll make 0 the good outcome. So you get a past data, like from last year. You get this data. You get a couple of hundred of these or something like that. And actually, let's even just talk about what you do with this. We're actually going to fit A and B. So we're going to do a maximum likelihood estimation of the parameters A and B. By the way, once we have them, we can do interesting things. Because someone can arrive tomorrow at the hospital, we can evaluate their U, evaluate this, and for example, if this turns out to be +3, that's not good for them. If it's -3, I guess we can reassure them or something like that. That's okay. All right. So this is the idea. Now, how do you do this if you want to work out what the log likelihood is? Actually, it's nothing but the likelihood function is the product of these things, because we're assuming these are independent samples from a logistic distribution. So you take the product of these. If you take, which is this, And what we've done is we've simply reordered the samples so that the first k ones were the ones, I guess, who died in this case, and the last m minus k plus 1 or something like that, whatever this is, are the ones who didn't. So that's, you just reorder them. And in that case, you get the, I mean, you just take out the, you just multiply all this out. You can see that in the denominator, you always get this thing. That's for all of them. And the numerator, you take this, and you take the log of this. And this thing is the log of the product of the x. That comes out here as this affine term. And this one over here is minus log sum x. Now, of course, log, well, by the way, why did I call this log sum x? I'm going fast now, but someone want to justify? How did I know just immediately that this thing was convex?
Log of sum.
What is it? It's what?
Log of sum of exponentials.
Yeah, but there's a 1 there. That's 1 is exp of 0.
Right.
This is the log of e to the 0 plus e to the a transpose ui plus b, like that. Okay? So it's log sum exp. It's the 2-term log sum exp called with 0 comma a transpose ui plus b. Okay? So this is convex in this argument. That's affine. This whole thing is convex. And with the minus sign, it's concave. So this is concave. Okay? So that's the picture. By the way, if you want, you can actually draw this function as a function of ai transpose u plus bi. That would be called the logistic, well, if I put a negative sign here, which I haven't done yet, it would be called the logistic loss function. And it would be something like this. I wonder if I can get it right. Let's see, which do you want? If this is small, then that is, that's about 0, and it's that. So I think it looks like that. That's 0. I may have gotten that right. If it doesn't look like this, then flip it over. And if that doesn't work, flip it this way. And if that doesn't work, flip it this way again. So in one of those orientations with some number of minus signs and so on, the I guess actually people do logistic loss. They refer to it as this. It's a function that looks like that. Actually, this gets linear in this case, approximately linear. So anyway, but this is something to be maximized. So. But is this covered in, I know a bunch you've taken 229, CS 229, is this there? Come on. Where is logistic regression covered in? It is. It's got to be.
Yes,
What?
yes.
It is. Okay. All right. So. All right. So here's just an example. It's a super simple example. This is as with most examples that you can show on a slide. They're examples of what they're examples where you definitely did not need any advanced theory to figure out how these things work. Okay. So. If, in fact, there's only one explanatory variable, which is here, u, and then a bunch of outcomes here, then you definitely don't need anything advanced. I mean, just look at the data with your eye. So that's not the point of this. I'll give you some examples of where logistic regression works, where we're not talking what you do with your eye. So here's a whole bunch of data. It's 50 measurements. And each measurement consists of this. It's a value of u here, and then it's a 1 or 0. So that's all it is. I mean, this could be anything. All right. So, and you can see roughly the following: that when u is larger, you get more 1s. I mean, you can see that because there's a sort of a concentration up here and fewer down here. And you can see that if u is smaller, there's fewer. You're more likely to be 0. Okay? But you can see there's lots of exceptions. Here's somebody with a very low u that turned out to be 1. Here's someone with a very high u that turned out to be 0. Okay? So, oh, I should mention one thing. What do you imagine? Well, okay, let's. What this shows is A and B have been estimated. Now, A and B do nothing but control what here in the logistic distribution? B controls the point where this is neutral, and A controls the spread. It's the width of the transition zone. So A controls how stretched out this thing is, and B controls sort of where it is. And you can see that it has lined up, you know, about at what would be a very good decision point if you were forced to make a hard classifier here. It's lined up quite well as something that, you know, approximately separates, not perfectly, but approximately separates these cases from these. And this spread here tells you roughly where how much indecision there is. Okay? Let me ask you a couple of questions here. What do you imagine would happen if the data had looked like this? What if there were none there and there were none there? Okay? So basically there's this data and there's this data. What do you think? What do you think the first of all, what do you think? First of all, let's just talk informally here about what you think the logistic estimate is going to, the logistic maximum likelihood fit is going to be. Just draw a picture. What do you think? What's it going to look like? I mean, like this? No, it's going to be much sharper. In fact, it's going to be infinitely sharp. It's going to basically look like this. It's going to be a perfect thing like that, right? And the truth is, this thing can actually move left or right. It makes absolutely no difference. So the point is, if the data here is actually linearly separable, right? If there's a perfect classifier, that corresponds exactly to the logistic regression problem being unbounded. If you're doing maximization, it's unbounded above. Okay? So unboundedness above of the log likelihood. It means you get an estimate. It basically means you can make the log likelihood function as large as you want. Okay? And that corresponds to this perfect separation like this. Okay? So, I mean, you have to check me on this. So this is the, okay. So what would be uses for this? I am not quite sure, but I believe actually some of the best spam filters are done using logistic regression. I'm not, you hear both things. It's something called support vector machine, which we'll see very shortly, and logistic regression. So my guess, I think it's both. So that's how that works. There, of course, the dimensions are very different. They're not one, right? You've got like you've got thousands and thousands of features and things like that, and you're estimating over very, very large data sets. Okay. Does this make sense? So this is an example where it's not linear remotely, obviously. I mean, this here it enters in a very, very complicated way. If you like to think of this as a measurement or an outcome, works this way. By the way, I should mention to those of you in areas like signal processing and things like that, you might think, well, this doesn't have anything to do with me. Actually, I beg to differ. This is a 1-bit measurement. Okay, so this is exactly, well, with a particular distribution. You change the distribution, it's something else. So you will, if you do signal processing with low bit rate measurements, including, for example, single bit measurements, you will exactly get problems like this. Not quite this one. If it's Gaussian and then you take a sign, you're actually going to get, it's called pro-bit regression. And you get a different function here, but it's the same, everything otherwise is kind of the same. Okay? So, okay. So that was our whirlwind tour of a more complex parameter estimation, maximum likelihood estimation problem. So, okay. Oh, and let me mention, actually, with this one I can actually mention some of the cases where, the canonical cases where you get non-convex problems. And this you probably look at in machine learning and other applied classes and things like that. What would happen is you'd get a bunch of data samples like this, but for some of the samples, some components of the UIs would be missing. That's the missing data problem. And there, the resulting problem is not convex. Okay? There's some very, very good heuristics that you can imagine, like assuming a value of u, carrying out the regression, then going back, plugging in the most likely value, estimating u and alternating between these two, and these are all schemes that are used and so on. But okay. Now we're going to look at hypothesis testing. So how does hypothesis testing work? It works like this. And this is just, we go back to the simplest possible case. You can get very complicated other cases. like multiple hypotheses, not just one, but multiple ones. Sorry, two, but the single hypothesis testing case is actually quite simple. But anyway, so we'll go to the simplest one. This is where you have 2. And we'll just take a random variable on the letters 1 through m. So just very, very simple random variable. And what's going to happen is either a sample, which is literally, it's just an integer between 1 and n. It was either generated by the distribution p or the distribution q. So these are non-negative numbers that add up to 1. They're just vectors, actually, the p and q, the distribution, because we have a finite set here. So that's the question. I give you a sample, and I give you a sample, or I give you a couple samples or something like that, and your job is to estimate, was it this distribution or this one? Now, of course, this could be very easy. For example, if x turns out to be 1, and this is I mean, kind of intuitive, and p1 is 0.9, and q1 is 0.002, right? Then it's just intuitively clear. It's quite clear. It's a very good guess. By the way, not a perfect guess, but a very good guess that in fact x came from the distribution p and not q. Okay, so that's roughly. I mean, it's not that unobvious, you know, what to do here. As in these other things, it's not that it's intuitively unobvious. The question is, how exactly do you estimate, and how do you make a better estimator than an intuitive one? So we'll look at the idea of a randomized detector. So a randomized detector looks like this. It's a 2 by n matrix. So it looks like this. And what it means is this. Each column is actually a probability distribution on the 2 outcomes, like hypothesis 1 and hypothesis 2. Okay? And it says that if this is the outcome that occurs, you should guess 1 with this probability, or guess 2 with this probability. So that's the idea. Now, of course, often these things look like that, okay? Something like that. What this says is, if this is what you observe in x, you simply guess it came from 1. If this is what actually observed, you guess it came from hypothesis 2 or q. Okay? So if these are 0, 1 entries, it's a deterministic detector. And a deterministic detector is silly. It just means basically you have partitioned x, the outcome space, into 2 groups, where if the outcome is in one set, you declare that you guess it's hypothesis 1. If it's in the complement, you say it was hypothesis 2. I mean, that sort of makes sense. However, you can have something like this, like that. You can have something weird like that. That means if this is the outcome observed, you then go off and you toss a coin, and with 80% probability, you guess that it was hypothesis 1, and with 20% probability, you guess it's hypothesis 2. Now, by the way, this is sort of like randomized algorithms in computer science. This just looks weird. Like, why on earth, if you're trying to make an intelligent statement or guess what happened, it doesn't seem like gambling on your own is actually going to help anything. I mean, why on earth would you say, oh, tell me what happened? You go, excuse me for a minute, and get out a coin and flip it. It just doesn't look, something doesn't make sense. Which is kind of like in a randomized algorithm, right? When someone says, here's my problem instance, I'm talking now in computer science, and you say, how do you solve it? And you go, hang on just a minute. And you get out the coin and you start flipping it. And you say, what are you doing? And you say, no, I'm going to try to solve your problem. You say, my problem has no probability in it. I gave you a problem instance. Please give me the answer. And you go, hey, back off. Hang on. And you keep flipping the coin. It just looks, you know what I'm saying? I mean, after you get used to this intellectually, it's okay. But at first, it looks very odd. So the idea of having a deterministic detector, I mean, also, it's weird because you say, hey, you know, output 3 happened. And you go, yeah, sure, that came from hypothesis 1. And then the next day you say, output 3 happened. And you go, yep, that was hypothesis 2. So this looks very inconsistent and strange. Actually, we're going to soon see what a randomized detector can do for you. I mean, it's still weird, I guess. It's like, I don't know, if you're in physics, you have to, someday you have to either come to some equilibrium, for example, with like quantum mechanics and things like that. Does it make any sense? And same with these, so, or not. But then you just know it's an unresolved intellectual issue. Okay, so this is what a detector matrix is. And it describes a randomized detector. If you're uncomfortable with that, you just make it all 0, 1 matrix. Of course, there's a 1 in each column, and this becomes an encoding of a partition of the outcome space. Okay. Now, if I simply multiply this matrix T by P and Q, so if I take T and then I multiply by PQ like this, that's lined up like this, then I get 4 probabilities here, and they're actually quite interesting. So I'll tell you what they are. And I guess we should start with, well, I don't know, we could start with the 1-1 entry. The 1-1 entry is the probability that you guess hypothesis 1 is correct when in fact the sample was generated from hypothesis 1. So this entry is a good entry. It's an entry that you want near 1. Actually, if it were 1, it would mean that you would be absolutely infallible. You could never. This entry, let's go down and look at this one. This entry that's the probability that you guess hypothesis 2 when x is generated by distribution 1. Okay, so that's the this is a false positive. We're taking I guess hypothesis 2 to be positive. Okay, so that's a false positive. Now, we'll get to that. This one, this 2-2 entry, so these two add up to 1. I mean, they're like a conditional distribution, in fact. I mean, they're conditional probabilities. This entry is the probability that in fact the distribution was generated by distribution 2, and you guessed correctly distribution 2. So that's this one. Again, that's something you want 1. And this is, so these are the ones you want small, are these off diagonals. It's probability of false positive, probability of false negative, and you want those small. So in fact, what you really have here is a bicriterion problem, because what you'd really like, well, of course, you'd really like this matrix to be the identity matrix. That means you're absolutely infallible. That means whenever it comes from distribution 1, you correctly estimate distribution 1 and so on. You make no mistakes of any kind, no false positives, no false negatives. But you really have, in general, you have a trade-off between these two false alarm probabilities. Okay? And I guess there's lots of names for this trade-off. I actually don't know what it's called in statistics. I know what it's called in signal processing. It's called the ROC, which is the receiver operating characteristic, which goes back to like World War II or something like that. What's it called in statistics? Really? Maybe it came from you guys. Who knows? Doesn't sound like it to me, but anyway. Okay, so, all right, so that's the problem you want to, and we can actually talk about some of the extreme points. Let's see, how small could I make the probability of false positive be? And how might I do that? How small can I make the probability of a false positive?
0.
I can make it 0. How?
Always guess.
Yeah, you just guess 1 no matter what happens. Then in that case, you will never be accused of having guessed 2 when in fact 1 generated the sample. Okay? So that, by the way, that scheme also has another huge advantage, which is great simplicity. You don't have to even, you don't even have to listen to what happened to guess where it came from. So, and obviously I could make false negative 0 as well by simply always saying it's positive. All you do is you always guess guess it's negative always, okay, just period. And I think we got it wrong. You hear to make a no, sorry, that's right. You guess 1 here. You guess 2 always. Okay, so this is actually correctly viewed as a bicriterion problem. Okay, so it's a Oh, and by the way, what happens if there's multiple hypotheses like 12? What happens if there's 12? Let's talk about it. Suppose it's 12. Because this is not exactly complicated stuff. We're just multiplying matrices out. What happens in the case of 12 hypotheses? Wow, this would be a good homework problem or something like that. But so what happens? What happens? Yeah, you have a 12 by 12 matrix. And how many of these bad guys off the diagonal do you have?
144 minus 12, so 132.
Yeah, but some of them aren't. Oh, okay, that's fine. Yeah, that's fine. Okay, yeah. So rough, 70 or something like that, right? Okay, so we got a bunch of them, right? And so now you have a big trade-off where, and you might have strong concerns about, you might have different concerns about guessing hypothesis 3 when in fact the truth is the truth came from whatever hypothesis 2. And that might be one you really care about making low or something. And you can imagine actually then it would get interesting. But we're just looking at it in a simple case. Okay, so you end up with this. It's a bi-criterion problem. You want to minimize these two things. Subject to this just says the column sums in T are 1, obviously, and this says that they're non-negative. So this is obvious. By the way, notice that everything here is linear. So if this is a bi-criterion LP. Actually, it's a trivial bi-criterion LP. So let's scalarize it. So we put in a weight lambda. If you put in a weight lambda, you add this up, and this is silly. That's a linear function of T, of the entries in T. It's extremely straightforward. This says subject to that. It's not only, so this is one of those linear programs, I guess, one of those trivial linear programs that you can just directly solve. It's kind of obvious. In fact, you can optimize each column of T completely separately because that's linear and so it's separable in T. This is a sum of contributions from each column. The constraints on T are simply that each column is in the unit simplex. And then I think you just did a problem on that, or you did one a while ago or something. Anyway, and it's extremely simple how to choose. You simply choose this. If P is bigger than lambda Q, you choose the first hypothesis. The other way around, you choose this one. So you end up with a deterministic detector, and this is called a likelihood ratio, likelihood ratio test, because what you really do is you look at this, and you compare it to a threshold, and then you announce then you guess which distribution it came from. By the way, this extends to the idea of continuous distributions and things like that. So it's very old. It's from maybe easily the 20s or something like that. Is that right? Roughly? Yeah, 20s, I'd say. Maybe you're even earlier, right? This is...
I don't know. That's about right.
20s? Okay, let's just say the 20s, right? So, and it goes back to... so now you see you have a nice mathematical way to go back to the simple case. You look, how do you guess which one it is? By the way, if lambda's 1, then you simply choose whichever one is the more likely. By the way, we'll see what the lambda equals 1 means. Lambda equals 1, well, you can tell me. What does lambda mean here? What does lambda equals 1? Because a maximum likelihood test would simply choose whichever had the maximum likelihood. That corresponds exactly to lambda equals 1. What's the meaning in the bi-criterion problem for lambda equals 1? Has a very specific meaning. What does it minimize? That minimizes something for false positives and false negatives. Maximum likelihood. What is it? What is it?
Probability of error.
The sum, yeah. Which is otherwise known as if you put a lambda, if lambda is 1 here, it means actually that you're minimizing the sum of this and this. But the sum of this and this has an interpretation. It's called being wrong, right? So it's called an error. So you're minimizing the probability of error. That corresponds exactly to lambda equals 1. Okay? So, and by the way, this ties back to maximum this is sort of the justification for maximum likelihood. So you could say a maximum likelihood detector, you would then argue, well, you'd argue and you'd be correct, minimizes the probability of being wrong, and you're neutral. You're absolutely, false positive has the same weight as false negative. Is there a question?
For this, do we have to assume that there's kind of an equal likelihood of being distribution P and distribution Q?
Nope. We're doing statistics.
Okay, but I mean...
You're not even allowed to say that in statistics. Okay. I mean, if there are...
If you're Bayesian.
Yeah, if you're Bayesian, no, we're not doing that right now. So that's, if you say that in front of statisticians, be careful. You could be physically dangerous. If there are some Bayesians around in the room with you and they're large, you're safe. Go ahead and say that. But watch out.
Okay, so I guess it seems then that if we get a data point and there's and we look at P and Q, and
Right.
there's a very small probability that that data point came from distribution P, a very large probability that it
Right.
came from Q. But if we know that 90% of the time...
Right. By the way, you're already using, you've identified yourself as a Bayesian, and you'd be already in big trouble.
Okay, well,
Okay.
I don't
But
know.
no, that's okay. Okay, I'll tell you in a minute. Okay.
Okay.
That's you're safe here.
Okay.
Don't try this over in certain parts of Sequoia. Okay, so don't try it. Okay, but go on.
Okay, but anyway, if you then, if you know that 90% of the time it's distribution P, then even though it's a small probability that your outcome came from distribution P,
Right.
the fact that distribution P is much more likely should probably like influence your choice.
Absolutely. So actually, this is a very good point to say this. So we're doing statistics, and in statistics, there is no prior distribution. You can't say even something like this is more likely, or what's the likelihood of it being this or that. You're just neutral. Okay. By the way, I'm neutral on this. I'm not partisan in any way on this. Well, we have to be careful because a lot of people in machine learning in this room too, and I don't know where their sympathies lie. So a pure statistician would never. You're not even allowed to say something like, this is a more probable which one is more probable. The minute you say that, now you're doing Bayesian estimation. So now I should say this, that if you do Bayesian estimation, then instead of maximum likelihood, you do something called MAP, which is maximum a posteriori probability. Okay, and it's of course quite sensible if you have some ideas about which of these things. If I told you ahead of time, by the way, you could redo all of this, and it's very, very easy in that case. If you do things like saying, well, yeah, it could come from these two distributions, but in fact, with 30% chance it comes from P and 70 from Q. And you could work out everything that would happen here. And you'd want something called the max. Then you could actually talk about the probability of, the actual probability of being wrong, things like that. So that's it. Now the good news is this. By the way, we could have done that earlier as well in maximum likelihood estimation, like for example, here. We could have done MAP. All that happens is very cool. You add an extra term. So what is a log likelihood function, or a likelihood function, a log likelihood function, turns into a log of a conditional density. Then you multiply by the log of a prior density, and you get regularization terms here. So that's what would happen. So, but you need to know, just socially speaking, that watch out. You're treading on very dangerous. Just saying things like that could get you in big trouble. What's that?
I wasn't trying to start.
No, I'm neutral. I'm totally neutral. But just you could say that in the wrong place and be very sorry. So the good news is from the convex optimization point of view, they all lead to. So the way that would happen if I was if I had some Bayesians coming on one direction, if I had Daphne Collar coming on one side, and who would be the most extreme one in statistics? Who would? No. Who?
No.
Trevor, you're not going to name a name.
People are pretty flexible now.
They're pretty flexible. Yeah. Yeah. So that was the right answer. And I had a statistical fundamentalist coming in, a group of them coming in on the left. I would, for us, it's very simple. You just add a term here, which we would just say it's just regularization. It's regular, and they'd say that's not regularization. That's the log of a prior. And I'd say no, it's just this is just regularized maximum likelihood or everything like that. So anyway, so that actually, thanks for bringing that up because I just wanted to. I mean, actually, if you go to the book, it's neutral and I believe honest about what it says. It just says if you choose to believe that you're getting a sample from a parameterized distribution and your job is to estimate the distribution, that's a statistician. That's statistics. You can do that.
To be fair, Bayesians are also statisticians.
Are they?
What you mean is
Well, now you know who I hang out with,
frequentist
what they are.
versus Bayesian.
Okay, sorry.
It's frequentist is the
Frequentist. Okay, sorry. That's the right way to say it. Okay, yeah. So I'm not totally up on the details of these various schisms, but I do know that there have been a lot of wars about it and a lot of bloodshed actually over these issues. But for us, they're just all convex problems, and they're just innocent little extra terms that end up in here. So that was a very long answer to your question. But it's a good, just as a matter of safety to know. Asking that innocent question in the wrong place could get you into deep, deep trouble. So, not really, but actually maybe it could come to, well, we won't go on. All right. So, all right, so let's look at some examples now. Oh, we have our interpretation of maximum likelihood. Maximum likelihood says you scan outcome 3 has occurred. You scan the two probability distributions. You go to outcome 3, and you see which has the higher likelihood. That's a maximum likelihood detector. That corresponds exactly to lambda equals 1. Lambda equals 1 corresponds precisely to saying that you treat false positives and false negatives equally. Okay, that's maximum likelihood. That will minimize the sum of the two, so which is something like the probability of being wrong. Okay. Now, you could also do a minimax detector. You could say, well, I want to minimize the maximum of the two error probabilities. Now, this one actually, of course, it translates to an LP immediately. But this one actually, generally speaking, in fact, in the finite case, essentially always it always has a non-deterministic solution. And so let's see what that is. So here's an example where here's these two distributions, and it's kind of, look, anybody can figure out what happens here. If it's outcome 1, you should probably guess it came from P, and if it's outcome 3, you should probably guess it came from Q. Everyone's going to agree on that. Okay? And there's actually not much else here to do, right? There's two other outcomes. And, obviously if it's outcome 2, you should kind of lean towards saying it was 2, but you should equivocate or something like that. Something like that. Okay. All right. So here's the ROC, or receiver operating characteristic, although it's generally drawn this way, and I don't know why, but anyway, it often is. So here are the two. Here's the probability of false positive, false negative. We've already talked about these things. This one is the detector that simply, this says, you have 0 false negative. That means you just simply always say it's positive. You just announce it's positive, and you can have 0 probability of false negative. Here's the trade-off curve here. And actually, of course, it's piecewise linear. I mean, that's obvious because you're minimizing a piecewise linear function over some linear inequality constraints. So this curve, this region is polyhedral, and the vertices here correspond to different things. In fact, the vertices correspond to the 3 thresholds in lambda. Lambda is the slope here. And so as you vary lambda to get a trade-off curve, it's kind of boring, because if lambda is smaller than this, you get that point. As you increase lambda, you will click over to 3, this point. And it's just some point. I mean, these are the deterministic detectors, 1, 2, 3, and 4. As you increase lambda like this, it's always the same. Right at this point, you switch over to a different threshold. Then you keep going like this, and then eventually you get so high that the safest thing to do is simply to guess that nothing ever happened. And that way you will have 0 false positive, always. Okay, so there's not many points on the trade-off curve. But the minimax one, that's very simple. It's the maximum of the two. And the level curves of the maximum, this dashed line here is the line of equal false probability and false negatives. And you can see very clearly that it's not a determinant. It's right in between these two, and it is not a deterministic detector. So if you want to have a detector here which minimizes the maximum probability of making either a false positive or a false negative, then you're gonna have to use a detector, a non-deterministic, a randomized detector. Okay. Now, I mean, this is all kind of stupid looking cases like this. That's fine. But if you want to make this non-trivial, it's very, very simple. You just imagine something with 12 outcomes and vectors and probability distributions on 1,000 points. Okay, very, very simple. And now you want to decide on a detector. And now you start throwing in insane things like how much you care about guessing it's number 7 when in fact the truth was number 3. And you start throwing in how much you care about all these things, and all of a sudden it's not obvious exactly how to do this. Then when you solve an LP, you get something or an LP or whatever. Actually, it's always going to be an LP. When you solve an LP, you'll actually get a detector that will beat soundly beat, according to that measure, whatever your criterion is. Okay, so that's the picture. Okay, so that's that. There's a lot more you can do with minimax detector with detectors here, and there's a couple more topics in the book, which you will read about. Okay. Now we're going to look at our last topic in this whirlwind tours experiment design. This is quite useful, very useful, and I think not that well, in some fields it's not that well diffused, knowledge of experiment design. Even in areas where people actually often do experiments and get construct models from data and things like that. Okay, so experiment design goes like this. We'll talk about how it works. We'll do the simplest case, which is just linear measurements like this, and we'll just say that the noises are IID N01. You can change all this, but let's just do that. Well, the maximum likelihood or least squares estimate is just this, and the error is zero mean. That's x hat minus x is zero mean, and it has a covariance matrix, which is this thing. So that's the covariance. By the way, here the noises all have noise power 1. So the norm of A is something like a signal to noise ratio. And now I'm talking if you're in signal processing or communications. So that's because I just made the noises have power 1. So if A is large, if the norm of A is large, that's a very good measurement. It's a high quality measurement. It's a high signal to noise ratio. If the norm of A is small, if the norm of A is 0, that's a utterly useless measurement because it's just a sample from noise and it has nothing to do with x. Okay, so that's if you want to get a rough idea, larger A is larger signal to noise. That's what norm of A is. It's literally the signal to noise, something like that ratio, because the noise power is 1. Okay, all right, and I'm sort of assuming their norm of x is on the order of 1, but with that assumption, that just scales the signal to noise. It's still the case that if you double A, it's sort of twice as good from a noise point of view, standard deviation anyway, as if you hadn't doubled A. Okay, now this is the error covariance, and it's a sum of diags inverse. That's very interesting. Okay, so we can say a lot of interesting things about this. The first is, if that matrix were singular, that would not be good. Okay, and what that means is the matrix is singular. It means you haven't taken a set of linearly independent. You haven't taken enough measurements, basically. Sorry, measurements that span x. Okay, so that would be the case there. So if you've taken enough measurements so that the measurement vectors span Rn, then that means this thing is non-singular. And then you take the inverse. And of course, that's the error covariance. And now it's clear, now I'm going to be very rough here. To make this matrix, you want this matrix small. And we'll talk about what small can mean. It can mean lots of things. You want the matrix small. But roughly speaking, the first thing you want is you want what's inside it, since that's an inverse, to be big. Good. That corresponds perfectly. Because if A is big, if the A's are big, then that means you have high signal to noise ratio. And that makes this error covariance small. Now, the interesting thing is it's not scalar. It's actually matrix inverse. And that's very interesting because it means what the error covariance is not simply, it doesn't depend just on the individual A's. It's actually how they all go together. Okay? Oh, there's one exception. If the AI's are mutually orthogonal, then this inverse, you can just do it, change coordinates and do it, and they're independent. And then they don't interact in any way whatsoever. But in general, what this says is the following, is you take a bunch of measurements, those are characterized by A1, A2, A3, and so on, and then you calculate the error covariance, and the error covariance kind of depends on actually the geometry of the whole set of these things. I mean, this is kind of obvious, but that's the idea. And for example, if you want to make a confidence ellipsoid, it would depend on this covariance thing. Okay, so experiment design is this. It says I give you a palette of possible experiments you can carry out. So we'll call those V1 through VP, and these are just experiments you can carry out. And now your job is to choose some number of experiments that will make this error covariance matrix as small as possible. So another way to say that is, I give you a palette of possible experiments you can choose, and the simplest thing would be I'd give you 50 possible measurements, and I say you may choose 1,000 measurements from these 50. Okay, you can choose 1,000, and you want that choice of 1,000 from those 50 to be mutually maximally informative. Because what's going to happen is you're going to take all those measurements together, you're going to blend them, do least squares, you get all the good blending that least squares is going to do, and together they're going to give you an error covariance like that. So let's talk about some choices. If someone said, well, sensor 1 has the highest signal-to-noise ratio, so I'm going to choose all 1,000 measurements to have the signal-to-noise ratio 10, because all these others have signal-to-noise ratio 1. Any comments on that? Is it a good choice? If V1 has a signal-to-noise ratio of 10 and all the others have signal-to-noise ratio 1, then you can choose any of them. So you can. Why would you not always choose the first measurement? It's 10 times cleaner than any of the other measurements. So, what's the problem?
Matrix is not inverted.
Yeah, you do unbelievably badly here. Because if all the AIs are equal to V1, this thing is rank 1. And it is by a long shot not invertible. Everybody see that? So the point is, you're going to be forced. You can't do a greedy thing and just choose high quality measurements. It's actually something where you have to choose all of them together. Does this make sense? I mean, actually, if you're confused, it's probably because this is actually quite trivial and I'm just making it sound complicated. But anyway, okay, but I do want to point this out. Okay, so you can write this way. It's a vector optimization problem over the positive semi-definite cone. And here's what it says. So obviously it doesn't matter what order you choose the measurements in. That's clear because all you're going to do is sum these dyads here. You just sum the dyads. So it doesn't matter which measurement I do first. What matters, if I have 1,000 measurements to take, I have a palette of 50 choices. What matters is how many measurements of type 1 do I take, how many of type 2, and so on. And we're going to call those MK. So MK is the number of measurements of choice K I make. And so I get this problem here. Now the MKs are integers, and they have to be non-negative. And and they add up to my budget. Now, by the way, this is just the simplest version. I could also put a cost on each measurement. I could not only put a palette of measurements in front of you, I could also put a price tag on every measurement. And you could have a budget in money or time. And you'd get then this budget would be something different. I can add other constraints to this if I want. I can add a time, money. I can add all sorts of other constraints. This is just the simplest case where all the measurements are equal. You have you're allowed to choose m of them. Okay, now this problem here, if you just say experiment design, this is what experiment design is. It's this problem right here. Okay, and this problem in general is hard to solve. But there are some regimes where it's relatively easy to solve. The feasible set is essentially the set of partitions of M. And by the way, if M is really small, like 3, then this is pretty easy to solve, or 4, or something like that. Then this is easy to solve. The other extreme is when M is very large. Because what you do is you rewrite this way, and you let lambda k be mk over m. And this is now the fraction of the experiments, of the m total budget you're going to use, of which you will take experiment type, measurement type k. So this is this fraction. Okay. Now, I haven't changed anything here. Actually, the truth would be something like this. The real problem would have m lambda k is in z, like that. Okay, so this real problem, this is the problem that gets you back to that one. It says that the lambdas I choose have to be multiples of m is 1,000, they have to be multiples of 0.001. Right? So I comment this out because can't handle it, basically. So you comment this out, and you get, now you get something called, some people call it's the relaxed experiment design, because I've relaxed this constraint. You already know that because wait, is that on the current homework? I don't know, because we're working on homeworks like 1 and 2 ahead. Are you doing something with a relaxation and Boolean variables now? Okay, good. Then you know what relaxation is. Okay, so relaxation is commenting out the constraints that you can't handle. That's really what it is. There was a question. Yeah?
Yeah, I was wondering if you can't handle the first problem because it's not convex. Reason is like your M is not convex.
The only thing that's not convex is that.
Therefore, you can't handle it.
Well, you could, but not right now in what we're doing in the class. No, in general you can't. So these problems can be very, very difficult. I believe it is, but don't.
Because it looks like knapsack.
Yeah, I think I could make. I'm pretty sure I could make this NP hard, but there'd be no. I'd go to Google and type. I'd type experiment design NP hard, and there'd probably be 5 papers showing that versions of experiment design are NP hard. I'm guessing, but I actually don't know. Just to make sure.
We also get rid of that constraint if we could use like a stochastic experiment design.
Yes. Okay, so that actually is an excellent question. And so let me explain how this works. When you do a relaxation, I mentioned this to you because you're doing one now. Okay. So the way you deal with relaxation, it's a very good point. It's a good time to talk about it. I'll say more about it later in the class. But when you're doing a relaxation, now first let's say what the truth is. The truth is you have a constraint you can't handle and you just comment it out. It's kind of like the truth of why do you do least squares. You do least squares because you can and you know how to. That's why you do it, okay? Then you can construct all sorts of stories, some of which are sort of true, not true, you know. And someone says, why are you doing this? You go, oh, everyone, why? Maximum likelihood, asymptotically, blah, 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 estimator, Gaussian, blah, blah, blah. And they say, is the noise really Gaussian? You go, yeah, sure it is, yeah. You know, anyway, you do it. So, also, by the way, if you repeat those lame excuses often enough, you'll actually start to believe them. Right? So you'll actually, it started off as just you couldn't handle it. But then what happens is after you've been very successful doing least squares for like 15 or 20 years, you actually start believing it, that things are, you know, anyway. All right. So this is a great example. You're doing experiment design. You can't handle this, so you simply comment it out, and you're going to solve this problem here. Now, by the way, in this problem, you could get very close because you could bound how far can you be off if m is 1,000, right? So the point is, if you solve this problem with lambda being just a real number, you know, these are numbers between 0 and 1. It's a probability distribution. Each such number is at most 0.0005 away from an integer multiple 0.001. So you could actually bound that, right, in this case. So you could say, you could actually, you don't have to fall back on some totally lame excuse and something like that. But the alternative is actually better because it works universally. It was your suggestion, and it goes like this. When someone says, what are you doing? You say, well, I'm solving this problem here. And you go, yeah, but this thing has to be an integer multiple of m. And you go, oh, no, that's very unsophisticated. I'm actually doing what I'm really doing is it's stochastic experiment. It's like randomized. Actually, it's exactly like randomized detector. And you go, no, this is very sophisticated. This is how, you know, this is like, it's like a randomized algorithm, randomized detector. This is much more sophisticated than just committing to 179 of type 1, 28 of type 2, and so on that add up to 1,000. You go, no. This is much more sophisticated. I'm coming up with a randomized experiment design, and I'm going to come up with a probability distribution on the possible measurements. And then what I will do is I will ask for a measure. Each time someone asks, I can carry out a measurement, I'll flip a coin and do a randomized experiment, and I'll use those probabilities. Now, of course, this is totally lame, this argument, but it often works. So I do recommend trying it when you relax something and see if you get away with it, because it just makes things easier. So, did I answer your question?
Yeah, but one other quick one. Can you do better like that?
What? With this?
Using stochastic design, can you do better than deterministic?
Can you do better? Oh, yes, because you've removed a constraint. So you always do better, in some sense, right? I mean, the only problem with solving this problem and not the original one is when someone comes along and says, yeah, but I have 1,000 measurements. You got to come up with some numbers that add up to 1,000. And you go, yeah, well, 187.22. They go, what does that mean? I can't do 87.22 experiments of type 1. I can do 187 or 188. Which is it? So that's the problem. And you go, no, but the 22 is more sophisticated because see, if you had to do 100,000, you'd be doing 18722 or something like that. So anyway, yeah, I mean, in this case, if m is large, you can bound how far off you can be, and it's not a big deal. In the Boolean case that you're doing right now, by the way, it's often not the case that you can bound how far you're off. Okay, so, okay. All right, so this is the problem. And by the way, these things work really, really well. I should also add the same thing you're doing in your homework now, or are doing or will be doing shortly. The same methods work for experiment design. They work unbelievably well. So if someone actually said, choose 1,000 experiments to carry out from this palette of 20, you'd solve this problem, you'd get some lambdas, you'd just round them to numbers. Like you'd say, okay, 187 of the first one. And by the way, that would be a valid choice of experiment design, right? And it would have a certain value of E, which is a covariance matrix, okay? The relaxation gives you a lower bound. And then you'd say, someone could say, is that the optimal? And you could say, then you could honestly say, don't know. But I can't be more than 0.01% off. So it's good enough. So the same thing. You only know what I'm talking about if you've started on the homework. So, which is maybe not very many people. But anyway, we'll just move on. Okay. So there's the other question is, how do you scalarize the fact that it's a vector problem? So I mean, but it's more than it is a vector problem. It's covariance matrices. And by the way, in experiment design, you get interesting stuff, and it's just what you think. I mean, basically what happens is this. I'll just draw a confidence ellipsoid. You make one experiment design, and you might get this confidence ellipsoid. Okay? You choose another blend of experiments. If you choose another blend of experiments and you get this, it's very simple. The second was a better choice than the first. Okay, the period. This is the clear, unambiguous section. But in fact, the way it really works is something like this: you choose one set of experiments and you get that as your confidence ellipsoid, and you choose another set of experiments and you get this. Okay, and now you can say which experiment design is better. And the answer is it's total nonsense. It's a multi-criterion problem. Now, by the way, if you're estimating x1, which one is better? 2. Obviously, the second one is better, right? If for some reason you wanted to estimate something along this axis, obviously, that axis, then 1 would be better. Okay? That's it. So you have to scalarize this, and there's lots of ways to scalarize it. And each way to scalarize it, by the way, ends up with a name of experiment design. The most common one by far, many books written on it, is d-optimal experiment design. I'm guessing D comes from determinant, but honestly, I don't know. So the d-optimal experiment design, you minimize the log det of the inverse, or you maximize the determinant of the covariance matrix. Okay, so that's what you do. As a beautiful interpretation of the confidence ellipsoids, you are minimizing the volume of the confidence ellipsoid. Okay, so that's the way that would be the geometric interpretation. There's others. If you put a trace, if you minimize the trace of this, which by the way has another beautiful interpretation. The trace, by the way, is the expected is this. It's the expected value of x hat minus x true norm squared. So if you minimize the trace, and that's called A optimal design is the other one. And there's others as E optimal design, and they go on and on. Okay, so it's clearly, it's a convex problem because we're doing relaxed experiment design. It's a convex problem. You know what we should do? We should just do a homework problem on that. Now they know what relaxations are. Just super simple one. Sorry, we're behind on that one. We should do that, where you get the bound and then you do the design. Okay, we'll do that. So here, actually, I think I'll quit here, but we'll look at an example, just to see how this works, and then I'll talk about this last business. So here's some possible experiments that you can carry out. So these are the A's. So basically what it says is you're going to measure, you're actually going to make a linear measurement. Now notice that these things are farther out. They have a larger magnitude than these. That means that this is a set of sensors here that have higher signal-to-noise ratio than these measurements. Okay? Now, it should be kind of obvious what you really want to do, if possible, is to have high signal-to-noise ratio measurements which are orthogonal. Because if they're orthogonal, it turns out it's going to, when you do the inverse, the condition number is small, and big will translate to big to small when you invert the matrix, and so on. And so, sure enough, I think we had something like 20 possible the palette of experiments offered was 20. 2 were selected. And the 2 that were selected make tons of sense. Didn't select any of these because these measurements kind of do the same thing, but with a better signal-to-noise ratio. So these were opted for, number 1. Number 2, it chose these ones that sort of were farthest apart from each other, the measurements that were farther apart from each other. By the way, if you do things like GPS and stuff like that, these things will make perfect sense to you, right? These are them. It says you want to take measurements. In fact, you'd even call this like geometric gain or something like that is what you'd call this. So this is what happened. So obviously in this case you did not need to solve a convex problem to be told that you should take high signal-noise ratio measurements instead of low ones. And you should, if possible, take ones that are nearly orthogonal. You don't need that. Trust me. You have a problem where you're estimating 50 variables or 10 even, and you have 100 possible measurements. There is absolutely no way you can intuit what the correct mixture of what the right experiment design is. And the result can be very, very good. So, but anyway, I thought we already decided. You'll find out. Well, you'll do one. Okay, so we'll quit here.